which is trained on the ImageNet data set. And so you can just select an image, like let's say you select a dog. And so you can see that it is able to find the breed of the dog also, and with the 93% accuracy. So here, obviously, the model can have like a model can be inaccurate also. So that is why it is saying that by the 3%, it can be the Tibetan Mastiff also, or the flat-coated retriever. So in this way, you can try different images also, like this. Like here, the model is confused between the cello and the violin. So you can, or you can upload your image also. So in this way, you can infer, you can have the inference from the trained model. So any question on this? If not, okay.
Okay. So thanks, Arpan. So let me go back to the slides again. I hope these two kind of the demos give you a kind of a rough idea of what we are seeing in a, like a training uh, and the inference. I think you can see my screens. Yeah. I can just so those are like the high level concepts. But now if you take a look at some of the another example, like here, if you see credit card fraud detection. So this is very common these days. I'm sure some of you might have seen, like, let's say you suddenly do some random purchase, or you do land in a different country and then start purchasing, you get an email or a phone call from your credit card company saying there could be some unauthorized access going on. And this is a very big market. Here again, the idea is that can we come up with a model? Can we predict the probability of the fraud? And then there could be some humans being involved, like those agents and all. And then from there, you can actually identify whether there is a fraud is taking place or not. And you detect it, and then you talk to the person, and then trying to resolve it. There are a lot of other examples, like this is a traditional HPC example. If some of you have been familiar with like the scientific simulations, so far people have been doing, let's say you are trying to design an engine of an aircraft or a wing, you have so many different dimensions, so many different parameters. So might be, let's say I have 5 dimensions, and each dimension has 5 parameters. So I need to run like a 5:5 number of simulations. And that takes huge amount of time on the HPC system. So the question is, can we actually try to see, as we are running the simulation, if we are not getting some good results, can we learn from the simulation itself? Okay? So that we make our simulations more intelligent, so that we don't have to spend all those hours, but we still get the results. Here there is another example, like from a traditional arts category, let's say Picasso. Picasso has been a big painter, has painted marvelous pictures in the past. Can the machine actually learn how to paint like Picasso? So if I give a doodle, then can the machine actually, based on the learning, actually try to paint as if like Picasso would have drawn it? But of course, there are some ethical issues in all these fields. That I think we'll keep it aside a little bit for the time being. In this tutorial, we'll mostly focus on the technical aspects, but I also want to indicate that ethics also is a big issue, and many people are also working in the field in the same manner. So then this is a very simple example, another one, and it's just like the language translation. You land in a different country. Let's say I'm trying to buy something for my daughter, trying to identify the cookies and the contents. You can use a Google Translator to very quickly find out what content is there. And the biggest challenge is, of course, the self-driving cars. If some of you have Teslas, you would have seen, might be using it. Over the years, there have been a lot of advancements have taken place. So the question is, without the human involvement, can the car itself be able to detect the roads, the signs, the situations, and will be able to drive itself? Another example here is the medical field. In this case, I'll be trying to show some digital pathology examples, and in fact, later on, we'll try to show some concrete results. We have been working with some of our colleagues at the Ohio State University Medical Center. We'll actually show you how we have taken their data and really gone through the models and have trained. But the broad idea is that if you see a typical, if you go to a doctor, the doctor asks for some samples to be taken, and then these are taken traditionally in the early days. It used to be samples, it used to be converted into glass slides, but now they are converting everything into digital slides. And in any hospital, you have thousands and thousands of these slides. And an expert pathologist can quickly check it and then say, wow, this is the kind of the symptoms or this is the disease. But the pathologist time is very expensive. Okay? So the question is, instead of like the pathologist spending a lot of time, can actually machine help? So based on the history, let's say the 100 patients have come, as their samples are taken and they are being checked against the model with the database. And when the pathologist comes, the computer might be saying that, yeah, patient X might have this kind of disease. Okay? So that helps actually to cut down the time a pathologist spends on the slides, and that also reduces the healthcare cost. So this is a very big field which is evolved. So I hope this gives you a broad idea of all these applications. So now let's go into a little bit deeper. We are starting with like 100,000 feet, and then gradually we'll be going down and down to all the nuts and bolts of this field. So let's take a common example like a computer vision. Okay, that has been the traditional thing in the deep learning, a lot of image classification, object detection. So for many, the default answer is the convolution neural network. So what does this convolution neural network mean? So if you open up any deep learning papers, you'll basically see a lot of these kind of terminologies: convolution layer, convolution operation, activation function, pooling. So the idea here is that if I have an image like this image is divided into small pixels, and then based on those pixels, we want to extract the features. And then from those features, we want to create these models. There are some convolution pooling layers and fully connected layers. Then in the end, we want to, based on that knowledge, we want to identify whether it is trying to identify whether this image has a bird or not, it has a sunset or not, is there any other animal or dog or cat there or not. Okay? So that's how we are coming up with the model, so that we can actually, next time we have a similar kind of a picture, with the model will be able to predict it properly. So now let's go into down. What is a convolution operation? I'm sure all of you would have heard of this term in your high school classes. You would have done some basic linear algebra kind of courses. But if not, this is how it looks like. So let's say I have an input here, and we have an animation here. You can see. So there is an input feature map. This could be the original feature map, might be a 5 by 5. And then we are trying to do a convolution with a filter. That could be a 3 by 3 filter. It gradually moves and aggregates information from those pixels and then come up with an output feature map. And this is actually the most time consuming part. And this is where you'll see why the deep learning takes a lot of time. There's a lot of action taking place, not only with respect to HPC system, interconnects, but also in the processor architectures, how we can provide better instruction sets or better ALU design, floating point designs kind of things to handle these AVX instructions and all to accelerate these steps. So here, there's an example. Let's say I have an input feature like this. It has like the 10 means higher value is white, 0 is dark. Can we identify this edge? Okay? By machine. Okay? Our eyes are very powerful, and then we can actually identify, yeah, there is an edge here. But people have developed filters. So let's say you run a filter like this and do the convolution. Now you can actually try to get that edge. So that means you transition from like the low value to high, remain here, and then after that you go down. So you detect that, oh, there is an edge. So like this is just only one filter. Different filters will give different features. So in this case, it is a vertical edge. You can identify a circular edge, diagonal, all kinds of things you can extract. So here, just to give a complete example, I'm sure this picture, all of you would have seen this from the movie. So this is the original picture. So now the question is, can we actually do a convolution on top of it, there is a filter called Sobel filter. So now you can see on the right hand side. So you can exactly through your computer from this image, you will be able to extract all these edges. Okay? So it shows the powerfulness of all these, the basic image processing, the filter. So that actually forms a foundation, at least in the imaging side with respect to the deep learning. And same things now you can actually try to do for all other kind of disciplines. So with this kind of background, now let's try to see these are the operations, but how do we really build the entire software system? Okay? So here I'll try to hand it over to Arpan. He will try to go into the next section. But if you have any questions, I'll be happy to answer. Are there any quick questions? It'll be good if we interact, right? Instead of us just talking. Please feel free to ask your questions on the chat or the Slack, and we'll be very happy to get engaged in the discussion. Okay, so if not, then let's proceed. Arpan, you can continue.
Sure. I hope you can see my slides.
Yes.
Okay, great. So hello everyone. So now we have some basic idea of what deep learning is and what is the machine learning and their applications. So let's move to the frameworks that can be used to train such models. So over the years, a lot of machine learning or deep learning frameworks have emerged. The main objective of the machine learning or deep learning framework is to hide the complicated mathematics. So as we all know that in the deep learning, we have some complicated mathematics and as well as in the machine learning. So how can we train the model without having to implement all of these complex mathematical functions? So let me give you an example. So if you see this mathematical expression, this is called the sigmoid operation in deep learning. This is fairly a very, very common expression in deep learning. And if you try to write it in the Minerva program in the matrix multiplication format, then this will transform into this code. And this equation can easily transform into this very easy data flow diagram. And if you want to optimize this function uh, as a system engineers and researchers, we would like to optimize this expression so that we can run it really, really fast, which will translate into the faster training. So if we want to optimize this function, then how can we do it? We can use the techniques like data partitioning, multi-threading, or multiprocessing. So if we use the data partitioning method, then this easy data flow diagram can easily translate into a very complex one like this one. And this is only with the data partitioning. So as you can see that as we add more and more optimizations to the implementation, it will become very, very hard to do it. It will be very hard to code. So that is why as a deep learning researcher, you want to focus on your model rather than on optimizing the every bit of the DNN training. So that is why we have the machine learning or deep learning frameworks that optimizes uh, all the pipeline for you, the whole pipeline for you, and they provide a very easy to use functions so that you can use them in your model. So the current generation of deep learning frameworks have already saturated the peak potential of current generation architecture, be it CPU or a GPU. We are already exploiting all the codes available on CPU or a GPU. So how can we train the model faster, even faster? As we all know that the current state of the art models cannot be trained on a single GPU because of the sheer amount of computation required in training those models. So how can we train those models? Broadly, there are two strategies to deal with the current limitation. The first one is the parallel or the distributed training. If you cannot train it on a one GPU or CPU, You can train it on multiple GPUs. We have thousands of these processing elements available. So you can easily, if we can somehow train the model on all the GPUs, then we can reduce the training time. So this is called the distributed training. If we have multiple GPUs on a single node also, so we can have a parallel training, or if we want to use all the nodes, then it is called the distributed TNN training. On the other side, if we can't train on the current generation architecture, let's make a new one. Let's make a dedicated hardware architecture for deep neural networks. So in this way, we can train the larger models with, we can have a bigger memory, we can add more cores to the architecture so that we can train those models in really fast. So one thing that is common with all of the with all of these two strategies is that you have to modify the deep learning framework. For instance, if you have developed a very fast, very efficient and optimized architecture for DNN training, if your software or the deep learning framework is not using those features, then you will not get the best performance. So that is why you need to modify the deep learning framework so that it can use all of those exciting features. On the other side, if you want to do the distributed training, and if you have a very basic implementation of distributed training, then you will not get a very good performance or the scalability. So for example, if you are considering the computation and communication as a separate entity, then you will not get a very good scalability, because you will spend a lot of time in communication when you are training the model on thousands of GPUs. So that is why we need to overlap the computation and communication, and we also need efficient implementation of those communication primitives. So that is why in both of these strategies, we need to modify the deep learning framework according to the um, according to the implementation. So that is why the ML and deep learning frameworks will need to be enhanced for the both strategies. So let's let's talk about the machine learning framework. So we are going to give a very quick overview of a current machine learning frameworks and deep learning frameworks so that you can get the idea how you can train your model. So Scikit Learn is one of the most popular machine learning framework, and it provides the off-the-shelf machine learning algorithm functions that can be used directly in any application. So it is a part of a very rich ecosystem, and it can be used in conjunction with the popular libraries like the SciPy, NumPy, Matplotlib, and the Pandas. However, the main problem with the Scikit-learn is that it does not have support for the GPUs or the distributed training. So, which is perhaps the biggest disadvantage of Scikit-learn. And the machine learning framework is the XGBoost. It focuses on boosting algorithm. So it provides an efficient implementation of a gradient boosting proposed in 2016. Boosting algorithms are used in ensemble learning, which is a very popular machine learning technique. It has support for GPUs and distributed execution with other frameworks like Hadoop, SGE, and MPI. So on the other side, we have the Qml, which tries to fill the gap left by the Scikit-learn and provides the GPU and distributed training support for machine learning algorithms. So it has a similar API and is a part of a NVIDIA Rapids project, which is gaining a lot of attention nowadays. You can also use the TensorFlow, PyTorch, or MXNet for the machine learning models to train the machine learning models. However, they don't provide any inbuilt functionality. So there you have to implement the machine learning algorithm from the scratch if you want to use these deep learning frameworks. However, the one advantage is that most of these deep learning frameworks are portable. You can train then if you implement the machine learning algorithm in these frameworks, then you can easily run it on a CPU, GPU, or any kind of new architecture that is optimized for DNN training. So here we are giving just an overview of Scikit Learn, like as Dr. Panda mentioned in the previous slides, that we have different types of problem in machine learning. You may want to do the classification or the regression, dimensionality reduction or the clustering. So based on this diagram, you can select the best algorithm from the scikit-learn. So if you, let's say if you want to do the classification and you have less than 100K samples, then you might want to use the linear SVC and or the other types of algorithm. But if you have more than 100K samples, then you can use the HGD classifier, which is very, very similar to deep neural network training. So in this way, you can use the scikit-learn to train your model and choose the right estimator. Now let's talk about the machine learning frameworks. So since 2013, a lot of the deep learning frameworks have been proposed. Initially, the most of the deep learning frameworks were from the uh, academic groups like Berkeley Cafe or the Theano from the Montreal Artificial Intelligence Group. After that, when big tech companies like Microsoft or the Facebook saw that the deep learning has a lot of potential, so they started their own deep learning frameworks also, like Google TensorFlow or Microsoft CNTK. So we are going to discuss a couple of these deep learning framework. So Google TensorFlow can be regarded as one of the most popular deep learning framework in current time. It is open sourced by Google and it is also maintained by the Google. It replaced the Google's disbelief network. So before TensorFlow, Google had a disbelief framework and they were using it internally to train the artificial model. Based on the experience gained from the disbelief framework, they implemented the TensorFlow and open sourced it to the public. It runs on almost all the architecture you can get hands-on, be it CPU, GPU, TPU, mobile. So it is very portable. And it has two different APIs. So basically earlier versions of TensorFlow like TensorFlow 1.0 series was using the TensorFlow sessions and estimators. However, now with the TensorFlow 2.0 series, it has shifted to eager execution and the Keras library. So Keras is a high level model definition library. So you can easily define your model using the Keras, and it is very, very easy. Now, the second most popular deep learning framework is the PyTorch. So originally the torch was written in Lua, but as we all know that Lua is not very popular. So that is why the adoption was not widespread. So PyTorch is a Python adaptation of Torch and it is gaining a lot of attention. It has several contributors, but perhaps the biggest support is by the Facebook. So around the same time, the developer of Cafe moved to Facebook and they started working on the Cafe too. But after some time, PyTorch and Cafe both merged into PyTorch. And the key selling point of the PyTorch is the define by run approach. So the PyTorch is one of the first deep learning framework which proposed this approach defined by run. So in contrast to TensorFlow, the PyTorch let you run the deep learning framework as you design it. So let's say you have added layer one, you have like hundreds of layers in your model, but when you have designed the model, like when you design the first 10 layers, you can run it, which is not, which was not supported in the TensorFlow earlier. So this is what we call the define by run approach. And it was it was very, very helpful for the engineers who wants to debug the model and other things. So that is why the key selling point of the PyTorch was this approach. So there are other deep learning frameworks also. No offense to other deep learning frameworks you might like. So like we have Cafe, Keras, Theano, Blocks, Intel, PicDL, and the list keeps growing. And we have some big names also like the Livermore Big Artificial Neural Network Toolkit, LPAN, or the Destiny by the Amazon. Any question till now?
I had a quick question, Arpan.
Yeah, sure.
So where does Horowitz fit into all of these frameworks? Is it also its own distinct framework, or is it like a backend for these frameworks? I'm not very clear on that one.
Okay, yeah, very good question. Go ahead. So basically, Horowitz is not a deep learning framework. It is a middleware designed to introduce the data parallelism support into these deep learning frameworks. Okay, so so the Horowitz uses TensorFlow, PyTorch, or the MXNet in its backend. So it is not really a framework, but it is a middleware kind of a thing. So we are going to discuss the Horowitz in the later section of this tutorial, so don't worry about it.
Okay, thank you.
Did it answer your question?
Yes, thank you.
Okay, thank you. Okay,
Arpan,
so
there is a question. What is Alban? Can you talk a bit more about it?
okay, sure. So Alban is an interesting framework because in contrast to other frameworks which were designed for the single node first, like they were started with the single node performance and then they introduced the support for the distributed training. However, Alban was designed for the high performance computing systems. So it is by the Livermore National Laboratory, and it has a inbuilt support for the distributed training and several other parallelization strategies like the model parallelism, subgraph parallelism, spatial parallelism. Don't worry about these kind of parallelism. I'm going to discuss about them. But yeah, this is the kind of the support they are offering. So it is designed for the high performance computing systems. Uh, Anything else? Any other question? If not, let's go to the next slide. So there is a artificial intelligence statistics report published every year. So I just took two figures from that report, from the latest one. So here it is showing the trends with the machine learning frameworks. So since its introduction, TensorFlow is by far the most popular deep learning framework. So in the first figure, we are showing the GitHub starts over the years, and you can see that the TensorFlow is beating all other deep learning frameworks. So the second figure shows the trains for the other model, excluding the TensorFlow. So you can see that PyTorch is gaining a lot of attention since its introduction in 2017. And there is a one more framework, this dotted line. This is the Scikit Learn, and which is a machine learning framework. So Scikit Learn is a very popular. And if you want to do the machine, if you want to train or use the machine learning, then you should use the Scikit Learn. And when it comes to the deep learning, TensorFlow and PyTorch are the most popular deep learning framework in the current time. Okay, I think there is one more question.
No, Arpan. So I just posted link for Slack.
Okay.
So we would encourage all attendees to please join that channel and let's have a discussion. Any questions that you might have, let's have a discussion on that channel, please.
Yeah, and feel free to ask question here also. I would be happy to answer them live. Thank you. Any question till now? If not, let's continue. So now we have some idea about the machine learning and deep learning algorithm. Now let's see how we can train these models, where we can train these models. Okay, so it all started with the Alex Krasowski training the AlexNet model on the ImageNet dataset and showing the world that yes, the deep learning models can beat the state-of-the-art machine learning models. So when he proposed that model and showed that the deep learning model can beat the state-of-the-art models, then all the researchers started using the deep learning models in their research. So at that time also, he used two GPUs to train the model. At that time also, he was not able to train the model on a single GPU. So he introduced the parallelization. He implemented the distributed training by himself, and because at that time most of the frameworks were supported only a single fast GPU. They were not supporting the multi-GPU training. However, today the parallel training on multiple GPUs is being supported by the most frameworks. By the parallel training, I mean that if you have multiple GPUs on a single node, then you can do the parallel training. However, the distributed training is still upcoming, and there is a lot of fragmentation in the efforts. So, for example, you can use the Horoward, and you can build the Horoward with the MPI, Nickel, Glue, or gRPC. So there are a lot of options available when it comes to the distributed training. And after in the last decade, several deep learning models have been proposed, newer and the deeper deep learning models. And one thing that is common between all of these models is that all the state-of-the-art models cannot be trained on a single GPU. So at that time, when they were when they were proposed, they were trained on multiple GPUs. So even the current state-of-the-art models like GPT-3 or the AmoebaNet cannot be trained on single GPU. So that is why you need distributed training to train such models. And on the hardware side, we have different kinds of hardware like Havana, Nirvana, Google DPUs that are designed for the DNN training, or you can train your model on the smartphones also. So there are a lot of different options available, but in this tutorial, we are going to focus more on the conventional execution of on GPUs and CPUs. So we are going to focus on GPUs and CPUs for the DNN training as well as the machine learning. So we have all heard that our framework is faster than yours, or my chip is faster than your chip. If we want to understand the performance, we have to do it in a holistic way, because the performance depends on the entire execution environment. It is not that you just download the PyTorch library and you expect the best performance from it. Or if you're doing it on the GPUs, you just download the PyTorch and you expect the best performance. You have to download the other helper libraries also, like the Cuda, CUDNN, or in case of Intel, you have to use the MPALDNN. So that is why the isolated view of performance is not very helpful for the machine learning or deep learning workloads, as we have many architecture specific optimizations that need to be developed and properly used by the via helper libraries. So here I'm just showing the entire execution environment. So on the top, we have the deep learning applications like image recognition or speech recognition. And at the bottom, we have hardwares like the multi-many core processors. It can be Xeon, Xeon Phi, or the latest Cascade Lake or the Skylake processors. And we can have the many core GPUs like the Pascal P100 or the V100 or the latest A100 also. So if you want to train, let's take an example here. Let's say you want to train a model on a A100 GPU, and that model is convolution neural network. So you will be using a Cafe, TensorFlow, the PyTorch deep learning framework. If you use a generic convolution layer, it will not give you a very good performance, because when you are training it on the GPU, you have to use the CUDNN optimized convolution layer. So you need to install the CUDNN Qml libraries. In the same way, if you're training it on the Intel, then you have to use the MKL library or the MKL DNN. If you are using the BLAST libraries like OpenBLAST and Atlas, it will not give you very good performance. So let me share a very recent experience with you. So recently I tried DNN training on the ARM processors. So there are a lot of options available when it comes to ARM. When I was installing the PyTorch, you can install the PyTorch with the OpenBLAST, or you can install the OpenBLAST also with the other helper libraries. So you have to use all of those helper libraries in order to get the best performance. For example, on the ARM, you have ARM performance libraries, ARM PL, ACL. You have the ARM has also done something in the MKL, so you can also use the MKL on the ARM processors. And on the other side, they have different types of architectures also with different optimizations. So if you're trying, your one ARM processor can be different from the another one. So for example, you can have ARM processor in the Bluefield adapter, or you can have a general ARM processor, or you can have ARM processor from Apple. So That is why you have to use the right set of libraries to get the best performance. So this is the main idea. This is the idea we want to convey with this slide. Any question? If not, let's continue. So now we are going to talk about the parallel and distributed DNN training. Before talking about the distributed training, I'm going to give an overview of deep neural network training and explain the essential concepts so that we can understand the challenges faced by the parallelization strategies in the distributed DNN training. So here I'm showing a deep neural network with 3 layers. Like we have 3 types of layer: input layer, output layer, and the hidden layer. You can imagine the deep neural network as a function that maps the input to the output. So these hidden layers are the brain of deep neural network. The most of the computation happens in the hidden layer. So let's say you want to classify the image of a cat, like a image into a cat, and you want to find whether there is a cat in the image or not. Okay, so when you give it at the input layer, what will you do? You will calculate so you can imagine these small circles as basic mathematical functions which are applied. I'm going to tell you about what these mathematical functions are. So you can imagine these uh, circles as a neuron, which are some mathematical functions, and you are going to give the input to these functions, calculate the output. In the same way, you will calculate the output for this layer. And once you get the prediction, since this model is not trained, so that is why you will calculate the error and will back propagate the error to all the neurons so that we can calculate the so that we can update the parameters and according to the application and the data set we have. So in this way, you can train the model, and uh, so in this way we train the model. Actually, this we do the forward pass and the backward pass. So we all know that backpropagation involves the complicated mathematics, like when you are backpropagating the errors to the neurons, you need to calculate the different partial differentiation, because in order to calculate the gradients which are used to update the weights. So luckily, the most deep learning framework gave you a one-line implementation, so you don't have to implement any of those things, or you don't have to understand those things also. So you can just do the model dot backward, and the deep learning framework will do the backward propagation on the whole model. So what is the mathematical function which is used by the neurons? So it is not complex. It is just the weighted summation. So we are just going to do the weighted summation of input and just give the output. So if this is a weighted summation, then a combination of for a linear function will also be a linear. However, we know that in the real world, we have non-linear relationships. So how we can map the non-linear relationships using the deep neural networks? This is where the activation functions comes in. So activation functions introduce the non-linearity into the deep neural network. So what are these activation functions? Some like the ReLU is the most common activation function. It is just a fancy name for the maximum function. So the max function, you will take the max of 0 or the input. That's it. This is the ReLU operation. So there are other activation functions also, like the sigmoid 10H, which are used in deep neural network training. Any question on this thing, on the activation functions or the backpropagation? If not, let's go to the next slide. That is the learning rate. So here we are just introducing some essential concepts like the learning rate and the batch size, so that we can know the effect of distributed training algorithms on these parameters and the overall training. So I talked about the gradients, and the gradients are used to update the uh, weights. So the learning rate is a scaling factor which is used to scale the gradients. So just imagine the learning rate as the speed by which we learn new things. If you're, so let's look at this figure. On the y-axis, we have the error, and on the x-axis, we have the parameter. So for some parameter, we will get the lowest error. So suppose that earlier we are here and we calculated the gradient and it is pointing towards this direction. So if the learning rate is very high, then you can overshoot and reach here. And in the same way, you will calculate the gradient again, and then you will overshoot again. So if your learning rate is very high, you will never run. You will diverge. You will never converge to the minimum error. In the same way, if the learning rate is very low, then you will need too many steps to reach the minimum error. Like in this case, we need around 10 to 15 steps to reach the minimum error. So that is why we need the learning rate to be just right in order to reach the minimum error in the reasonable amount of time. You don't want to spend 2 years on reaching the minimum uh, point or finding the minima. So that is why we need the learning rate to be just right. Now, the another essential concept is the batch size. So there are different types of gradient descent algorithms. The first one is the batched gradient descent. So suppose that you have 100 samples in your data set and you want to train a model. What you can do is you can show all 100, you can do the forward pass on all 100 samples, then do the backward pass. And after doing the forward and backward pass on all 100 samples, then you will update the weights. This is one approach. The another approach is the stochastic gradient descent, in which you take one sample, do forward and backward pass, and update the parameters. So we are updating the parameters more frequently in the stochastic gradient descent and compared to batch gradient descent. We have there are issues with both of these approaches, because in the stochastic gradient descent, we are not utilizing all the compute power. Since we are only doing the forward and backward pass on one sample, we are not able to parallelize the code that much. So we are not using all the compute power. And another reason is the effect on the training. If you just do the training on the one sample based on one sample, then there will be a lot of noise, and that will create a jitter in the learning curve. On the batch gradient descent, if you suppose that if you have 1 million images and you are waiting to process 1 million images to do just to update the parameter just once. This is not very efficient, as we all know that we need several steps to reach the minima. So that is why we cannot use the batch gradient descent. So we have something in the middle called the mini batch gradient descent, which is like if you have 100 samples, you can take 10 samples from the data set, do the forward and backward pass on those 10 samples and update the parameters. So this is the mini batch gradient descent, and we are going to use this one for the training. And one full pass over the data set is called the epoch, and we need several of these epochs to train the model. Any question? Let's make this tutorial interactive. So please ask the question if you have any. Okay, so now we know the TNN training, and we know that larger and deeper models are being proposed every day or every week. So we started with the AlexNet model, which had only 7 layers. Now we are at AmoebaNet, which has like thousands of layers. And so that is why we are increasing the memory requirement as well as the computation requirement. The larger models that we have right now cannot fit inside the memory of a single GPU. They are so big. GPT-3 is so big that it cannot fit inside the memory of GPU, in the memory of one GPU. So that is why you cannot train it on one GPU. Even on 2 or 3 GPUs, you cannot train it. So that is why the single GPU training cannot keep up with the ever larger model, and the community has moved to multi-GPU training. But we all know that there is a limit to multi-GPU training, because we cannot have like thousands of GPUs on a single node. So that is why we need distributed training. Sorry, is there a question?
Yeah, Arpan, there is a question there on the large batch sizes.
There
So
is a
the
trend
question,
towards the large.
go
Yes.
ahead. Go ahead. Go ahead, please.
Okay. There is a trend towards the large batch size. Is there a reason why? Can you please explain the question again? What do you mean by it? Or Amir, if you understood the question, can you please
Yes,
tell
so
me?
Arpan, in the literature and in the industry, people who practice deep learning, they would want to have large batch size, you know.
Yes.
So what is the reason for that?
Okay. That's a very good question. Please give me 5 more minutes to answer this question. So I have few more slides. So and those slides will automatically answer your question. Okay. Thank you. So just give me few moments. Okay. So now, when should we use the distributed training? Should we use it for all the model sizes? Well, the answer is no. So if you're so here we are showing showing a figure with respect to network size and the data size. If you have a small, if your data set is small and your network is also small, then you can train it on a single machine. You don't need distributed training. In other words, if you want to train a model on MNIST data set or the Cypher data set that has only 60,000 samples, you can train it on a single machine. You don't need distributed training for that. But if you want to train a model on a very large data set and the model is also very big, then only you need distributed training. If you have if you have a smaller data, bigger model, then you will go into the underfitting. And if you have a bigger model but a smaller data set, then you will go into the overfitting regime. So what are those things? Let me explain it. So let's see let's see this one. On the x-axis we have the input, and on the y-axis we have the output. So we want to train a model that predicts these points. Okay, as we can clearly see that this is a second order polynomial. Okay, so if we want to train a linear polynomial, like the linear line on this model, it will not give us the best accuracy. So this is the underfitting. The model is not complex enough to find the relationship. Okay, if you are training a higher order polynomial function like the 7th order or the 8th order, then it will also find these. Then it will be like this. We don't want this because these are the noises. So that is why we want the model to be balanced. We want the model to be just right. We want it to be the second order polynomial, not the third or fourth. So this is the overfitting and underfitting. Okay, so let me get back to the problem of large batch size. So in the community, we are seeing people are working on large batch sizes. The reason is that when you are doing the distributed training, the batch size increases. When you double the GPUs, you also double the batch size. So that is why we are seeing a lot of efforts going into the large batch size training. Why? Let me tell you. So this is a study by the Facebook folks where they studied the effect of batch size on the overall validation error. So as you can see that till the 8K batch size, there is no effect on the validation error. But if you go beyond the 16K or 32K, then we are seeing the validation error is increasing. In other words, the performance of the model is decreasing. Okay, so that is why a lot of effort is going into this direction to solve this problem so that we can train the model with the larger batch sizes. So this is a bit older study, but it conveys the message. And currently we can train the ResNet 50 model on a ImageNet dataset with the batch size of 64K or even the 80K, something like that. So this is the reason we are seeing the train for the large batch size. Does it answer your question? Can you say yes, no, perhaps, maybe? Okay. So here, yeah, so here I'm showing another graph which is showing that the large batch size is good for the speed. As you increase the batch size and as you add the more GPUs to the DNN training, the overall training time decreases. So as you can see that it is decreasing from 200 seconds to just 50 seconds, but there is a limitation. So this is a older graph. So we are going to show you the newer graphs also, newer trains and the scalability numbers. So let me talk a little bit about the polarization strategy. So how do we do the distributed training? We talked about the DNN training. We talked about the problem of large batch size. We talked about the learning rate. But how do we do the distributed training? How do we use all the GPUs to train the model? Okay. So broadly, the polarization strategies can be divided into three categories: data parallelism, model parallelism, and the hybrid parallelism. In the data parallelism, we replicate the model on all the machines. So that is why the model has to fit inside the memory of a single machine. So here we are replicating the model. We are just copying the model to all the machines with the same weights. Okay. After that, we are so don't worry about it. I'm going to explain the data parallelism in more detail in the next slide. So we are going in data parallelism, then we distribute the data. On the other side, in the model parallelism, we are going to distribute the model itself. So the model and hybrid parallelism are used for the models that cannot be trained on a single GPU. In other words, that cannot fit inside the memory of a single GPU or a machine. So if your model is very big and you cannot fit it inside the memory of a single processing element, then you have to use the model or hybrid parallelism. So what is model parallelism? So in the model or the layer parallelism, we divide the model at the granularity of the layer. So here we are placing the layer 1 on the machine 1, layer 2 on the machine 2, layer 3 on the machine 3, and so on. So this is the model parallelism. And in the hybrid parallelism, which is the hybrid parallelism combines the data and model parallelism. So here we are splitting the model on 4 GPUs, and then we are replicating them on several machines so that we can get the good scalability. So basically use the lowest amount of GPUs to fit the model. So if the model can fit in on the 4 GPUs, then place it on the 4 GPU and then replicate the same configuration on other GPUs. This is the hybrid parallelism. Okay. So let's talk. Let's talk about the data parallelism in more detail. In the sorry, is there a question? Okay. So in data parallelism, we divide the data among the GPUs. Okay, here I'm showing it for the GPU, but the same theory applies to CPU or the other architectures. Okay, so we divided the data set and we replicated the model. So the parameters here means the model. Okay, so we have replicated the model on all 4 GPUs. And suppose that, let me take an example here. Suppose we want to train this model with a batch size of 128. So we are going to give first 32 samples to GPU 0, next 32 samples to GPU 1, and so on. Okay, we will do the forward and backward pass simultaneously on all the GPUs. After doing the backward pass, we will have the local gradients, because since we have like different data on all the GPUs. So that is why the gradients will also be different. So we are calling them the local gradients. Okay. So once we have these local gradients, we are going to use the MPI all reduce operation. What is the MPI all reduce operation? It is just the element wise summation operation. Okay. We are going to sum the buffer element wise. After doing the MPI MPI all reduce, we will get the global gradients, and these global gradients will be used to update the parameters. Since MPI all reduce makes the output available to all the processes, so that is why we will have the same gradients on all the machines, and this can be used to update the parameter, and then we will repeat this process. So very easy. Data parallelism is very easy to understand. Is there any question on this?
Yes, I have a question.
Yeah.
On a global gradients on the left, is it
Yes.
merging all the local gradients?
On the left.
In other words, do MPI all reduce merges all the local gradients and then replicates them?
No. Okay. Yeah, I got it. Okay. So it is not merging the local gradients. So suppose that you have a local gradient is of size 100. Okay, you have a array of 100 elements. Let's say, let's take an example here. 100 elements of local gradients on each GPU. Okay, so MPI all reduce will do the sum element by summation operation. So the first element of element of array on GPU 0 will be added to the first element of array on GPU 1, 2, and 3, and the output will be available to all the processes. So this is the element-wise summation operation. Don't worry about it. We are going to explain the MPI all reduce in more detail. Okay.
Yeah, I got it. Thank you.
I have a question or kind of an observation. So it seems like you're pulling apart this problem so that it's going to be highly network bound because the compute operations are very quick. Now, has this been even, has it been benchmarked on its performance and where the bottlenecks end up being?
Yes, that's a very good question. So basically, this is just the figure, like we are showing the computation to be very small, but in fact, in reality, the computation, like doing the forward and backward pass, will take a lot of time. And when it comes to the communication, we are not going to separate. We are not going to do first computation and then the communication. We are going to overlap the communication with the computation so that we don't see those bottlenecks. So one of the major bottleneck of data parallelism is obviously the MPI all reduce operation. So that is why a lot of research has went into optimizing this communication primitive. And in the later section of the tutorial, we will also show you like how communication runtimes have optimized this primitive. And we will also show some benchmarking numbers.
All right, thank you.
Okay, thank you. Anything else?
How are the parameters updated? Who updates the parameters?
All the GPUs will update the parameters. So all the GPUs have a copy of parameters, okay, on in their memory. And after calculating the gradients, we have a weight update rule. So it is just like W plus gradients into learning rate or something like that. That's it. So learning rate is a scaling factor for the gradients, as I have explained earlier, and in this way we update the parameters. So this is not
each of the GPU has to send the global gradients to the other GPU, so each one of them can do the computation locally.
Yes, that's right. So MPI all reduce operation makes the result available to all the GPUs. Okay, so it makes the result available to everybody. So you don't have to send anything after the MPI all reduce operation. So it is going to compute the summation operation. It will do the summation operation, and then it will send the result to all the GPUs. So after this operation, you will have the result on all the GPUs. So there is no need to send the data. Okay.
Yeah, I mean, just to understand, we'll go into more details, but the MPI all reduce itself is a distributed algorithm. So we need to see that it takes the data and performs several steps and then gives the results back. Okay.
Yes.
I had a question. So do we know why large batch sizes give lower accuracy? I don't know if it's like an implementation specific answer.
Okay. So the broad idea is let's say if you have a smaller batch size of 30, let's say, let me take an example. Okay. If your data set has 1000 samples, 1024 samples, and you are training with a batch size of 128. Okay. So you are going to update the model 10 times here. Sorry, 8 times. Okay. You are going to update the model 8 times here. And if you increase the batch size in an epoch, you will update the model 8 times. But if you increase the batch size to 512, then you are going to update the model only 2 times in an epoch. However, you are increasing the processing speed, but now you may need more epochs to train the model. Does it answer your question?
I see. Okay. So the graph you showed in slide 42, the epochs, number of epochs for each of those points is the same.
Yeah, it's the same. Okay. And there is one more thing. After some time, averaging, this is the broad idea, but there's something else is also going on in the background, and we cannot answer it, right? So it is. We are still trying to find the problem, why exactly the large batch size. If we just keep on using the large batch size, what is the problem here? So sometimes there are the approaches like warm-up steps, and which helps in the training. So it is a kind of a question to the DL community also. Okay. And from thank you. Any question? Any other question? Okay, thank you. So now Amir will discuss the distributed machine learning algorithms.
So Arpan, there are a few questions on Slack. So
sure,
have a look.
Sure, either. Thank you.
Right. So in this next part of the tutorial, we are actually going to change gears and now start talking about distributed machine learning algorithms. And essentially, I will use a lot of the material that Arpan has already discussed. Some of the challenges, they are just the same. But now, instead of talking about a deep neural network, we are talking about, machine learning models. And machine learning models, traditionally, they are known that they are not as compute intensive as what deep neural networks are. But however, we see that, using parallelization, dividing up the input data, or what Arpan has explained, what is called data parallelism, using that helps in solving machine learning problems as well. So in this slide, if you focus, I'm just talking about a very simple, very well-known machine learning algorithm, which is called k-means clustering. So if you focus on these 2D points, we are actually given a set of 2D points, and our task is to divide this into 3 clusters essentially. So we are initially given these 3 diamonds, blue, green, and red. They are basically called centroids. And the ask here is that we are asked that, divide the input points into, 3 clusters essentially. So this input can be changed. We can be asked to, categorize these data points into 4 clusters, 5 clusters. So this K essentially in the K means is an input provided to the algorithm. And as you can see, there are mainly 2 steps involved in the k-means algorithm. And the first step here is that, we are already provided a number of input centroids. These are called center of clusters. So we go through all the data points. There is essentially going to be a for loop, and we are going to compute distance of each data to, the centroid out there. So for example, in this particular case, there are 3 centroids. So for each of the particle, or for each of the data in this data sets, we are going to calculate, which is the centroid I'm closest to. So once we have done this computation for all the data points, we are in a position to make this decision, like, which cluster do I belong to? right? So in each iteration, then I will do this repetitively, because as we compute, are belonging to which cluster we belong to, we will realize that the center of the cluster is essentially changing. So as you can see, the data points are not changing, but the diamonds or the center of the cluster, that essentially gets changed or gets updated in every iteration of the algorithm that we execute. So this is how a sequential k-means algorithm is going to operate. But obviously we can increase the total number of data points, or we can also increase the number of dimensions. So for example, in this case, we are only talking about 2 dimensions, X and Y, but we can be given a space that is, let's say, 10 dimensional or 100 dimensional. So in that case, obviously the computation is going to increase, and there is a good case for dividing this into, or for utilizing multiple processors for doing this. So in this case, for example, let's imagine that we just have 2 processing elements. First one we are calling processing element 0, and the second one we are calling processing element 1. So let's say we are just given the task to use 2 processing elements to do computation here. So in this case, one of the naive way we can do this work is that we can divide the space into 2 parts, right? So all the data points that belong to the north region, they go to process 1, and all the data points that belong to the south region, they go to process 1 for their computation, right? So this is one way we can achieve parallelization. But this is obviously not ideal, because we have more work to do for processor 1 than less work to do in processor for the second processor. So in this case, maybe if we take the total number of particles, divide them into 2 pieces, that might be a better way of doing what is called domain decomposition in parallel computing. But anyway, just for the sake of example, I've just I made 2 rectangles where you can see that this input data is divided into 2 pieces. And in this case, each processor now is going to do this calculation of computing centroid individually, right? So each processor has information about the centroid. So there are 3 centroids there. We are given 3 centroids. So for all the local particles for each processor, they're going to compute distance to all, to these 3 centroids out there. And then they're going to classify their own local particles into these 3, clusters. But obviously we are going to require some kind of global knowledge. And again, MPI all reduce is going to help us with that. And the communication done here is actually, we are exchanging information about the centroid. So we are telling everybody that, here is an updated information of the centroid, of the center of the cluster. And later, we can recompute centroids after, doing MPI all reduce, and we can, update which data points belong to which data cluster. And k-means is somewhat straightforward algorithm to parallelize, as the results here are depicting. So for example, so this is on a NERSC supercomputer called Hopper. And the blue line here is the speed up for 32 dimensions. The red line is for 64 dimension, and this green line is for 128 dimensions. The x-axis here is the number of MPI cores. So from 512 to 1000 to 2000, 4000, 8000, and 16,000. And the y-axis here is essentially the computation time. And as you can see, as we are increasing the number of MPI cores, we can see that the execution time is coming down. So on the right-hand side, we are plotting the converse graph. We are plotting the speed up, which is the inverse of execution time. So as we can see, as we are increasing the number of core, the speed up is actually increasing. So it's actually straightforward to implement, or parallelize k-means kind of machine learning algorithm on parallel systems. So obviously, if you are going to use machine learning for your work, we will not start from scratch. We will not implement k-means ourselves, because there are already existing libraries out there that are doing a great job in doing that. So Arpan has mentioned Scikit Learn is one. Here we are talking about how can we now use, let's say, something like Scikit Learn on any other machine learning library and use it on multiple computers. So in this context, so for example, if you're relying on, if your sequential code is, let's say, in Scikit Learn, it should be possible to parallelize this using something called joblib, right? So this is going to support multi-threaded and multi-process execution. So Scikit Learn already has built-in support for joblib. Similarly, there is another set of machine learning library called gradient boosting libraries like XGBoost. So if you're running gradient boosting algorithm or utilizing one of them for doing a training, in that case, it is possible to run it on cluster of nodes, and there are technologies like Dask that we are going to talk in much more detail later, Ray or this, let's say, AWS Yarn, or let's say Apache Spark. We can use these technologies to parallelize our machine learning algorithms. More recently, there has been a library called Qml, which is actually a GPU version of, let's say, Scikit-Learn, because NVIDIA is running this project, and what they have done is that they are now writing, different versions of machine learning algorithms for the GPU platforms. So if we are using Qml, for example, in that case, we can utilize, something like Dask again, which is a big data computation framework, or NVIDIA's Nickel communication library for running or utilizing multiple computers or systems for doing, our training for our machine learning algorithms. So with this now, I will now move on to the next section of the tutorial, which is data science using Dask. So Dask is a popular task distributed computing framework. So essentially, if you're going to use, let's say, multiple laptops or multiple computers, the problem that you're trying to solve, let's say, is so big that it doesn't fit a single computer, or maybe the data that you're trying to process is so big that it doesn't fit a single computer. In that case, you will obviously go to start thinking about using a cluster or multiple computers or multiple PCs or laptops in parallel. So Dask is a technology that will let you do that. And this is very popular among Python programmers. So because this is written in Python, and it allows Python applications to scale from, let's say, laptops to high-end systems. Under the hoods, it basically builds a task graph that is executed lazily on parallel hardware. And one of the strengths of Dask ecosystem is that it extends popular data processing libraries like NumPy, Pandas for parallel environments. A Dask distributed library, as I mentioned, supports parallel and distributed execution. Under the hoods, it uses this async IO package that essentially manages parallel and distributed execution. We will talk more about this later. But as far as the communication backends is concerned, so Dask comes up with a TCP and a UCX. So UCX is a communication library. It already comes with those communication backends. But as part of our work, we have actually introduced an Mpi-based communication backend that can also be used for Dask. So we will talk about this in more detail later in the tutorial. And some of the other data science frameworks include Apache Spark and Ray. But obviously in this tutorial, we are limiting our scope to Dask. And this is the execution model typically followed by Dask. So there is a central entity called a scheduler. So, and this is the first process that, if you're parallelizing your work with Dask, this is the first process that will come up. And then, there will be multiple workers that will connect to the scheduler. So for example, now let's say I'm trying to use 4 laptops or 4 systems to do one of the computations that I'm interested in. So what I'll do is I'll start scheduler on one of the laptops, and then I will go start workers on all these other laptops that I have. So, and together the scheduler and the worker, they are now basically going to become a Dask cluster. So at the end of the day, what's happening is that through this client, I can now submit my job, whatever I'm interested in, to the Dask scheduler, and the Dask scheduler will then coordinate execution of this Python program that you're interested in, or your application, to all the workers that are connected to it. So Dask is pretty dynamic in the sense that these workers can come and go. So let's say if there's a failure, or if one of the worker is not responding, the scheduler will just simply reschedule that execution, and it will, one of the other workers or the compute nodes will take over that job. So with this, I will stop talking.
I think what we can do, Arpan, we'll take a break, but before the break, let's show the account setups and all for the hands-on exercise. Arpan, would you like to do that?
Sure, Dr. Panda. Give me a couple of minutes.
Yeah. So as I indicated, like we have a GPU cluster here. Towards the end, we'll be trying to do some hands-on exercises. Arpan will show you how to create accounts. There are already accounts. You just have to claim one. I think it is 119 slide number.
Yeah. 1 second.
So please create an account, and then there are different exercises. But there is a lab 1, which is starting from slide 120. That is like just totally setting it up. We'll not try to go through that because that takes a little bit more time. But let Arpan you explain. Yeah.
Sure. So we have a OSU RI2 cluster, so you can use we will give you the account name and the password, and you can just claim a password from here. I will also show you. So you can just SSH using that account, using the terminal. You can SSH in this way. If you're using putty, then you can paste this one into the host name, and then use this one as a password. So this is just a password for this account. If you let me share my screen.
Yeah. So Amir posted the link also on the chat, so you can directly go there to the Google Doc.
1 second, just.
I did. Yes, I have already posted.
Yeah.
So chat docs. Let me open it. Can you see the screen? I don't think you can. Okay, now you should be.
Yeah.
Okay, so this is the document. You can claim a account and a password from here. So I have already claimed mine. This is RI201 username. If you want to, you can claim just any account and just put your name on this, so that others don't use this account. So once you claim this account, then you can use the SSH command to log into the cluster.
And use the corresponding password. Like
Yeah.
if you have RI2 tutorial 07, so please use the corresponding password tutorial 07.
Yes. So please don't use the password from the PDF or the slides. Please use the password from here according to your username. So
and then so might be the lab 1, which we will not be doing, but people can, those of who are interested, they can get started with that, and we'll come back to the lab 2 onwards. Okay.
Yes. So those who are interested in lab 1 can do it. It is not mandatory. So you will be in this directory once you log in, and we have the lab 1 where we set up the environment for the distributed DNN training using the PyTorch, and Horowat. So we have a detailed steps in the README file also. So you can find the README file in the lab1 directory, and once you open it, it has all the commands you need to install and create the environment. So this is an optional lab. We are not going to use the lab 1 in the subsequent labs. So don't worry about it if you're not doing it. Okay.
So I think with that, let's take a short break. Might be now it is 1:36 Eastern. Let's get back at 1:50. Okay. We'll post it in the chat, and we'll be monitoring also on the chat and Slack. So if any one of you have questions, please feel free to post those things.
Just one comment on the lab 1. We are going to install the PyTorch on the CPU because we don't have the nodes available, GPU nodes available for all the users here. So that is why we are in the lab 1, we are installing the CPU version of PyTorch, but installing the GPU version is not hard. If you just go to the PyTorch, you can get the command for the GPU version also. So don't worry about it. Okay, thank you. So that's all. And let me know if you have any issue in lab. Okay.
Thank you.
And there is mainly a README file. Once you log in, there is a README file. So that has all the instructions. So that is the best guide for going through the practical material.
Yes. So
And the slides
we
are again available. Those who joined later on, you just look at the top and it was posted on the chat and Slack. Please feel free to download the slides. Thank you.
Hello.
Hello. Hello.
Oh, hi.
Yeah.
Yeah, I tried. I can't get, it looks like I can't create a directory, permission denied.
Sorry.
On the, okay.
Yeah, so
Hello?
I might not be able to do this because it says RI2 TU2 tutorial 03,
Yeah.
RI2 tutorial 3, permission denied, cannot create directory.
Hello? Can you hear me?
Yeah, Arpan, can you take a
Yeah.
look what is
Yes.
happening?
So
Yeah,
please,
I'm actually on,
so
yeah,
you can,
I'm on op tutorials, DL tutorial 21,
yes. I can hear you.
lab 1, and I'm there.
Okay. So
And what I did, I sourced the MD file.
So
Hello?
can we take this on team?
Yeah. Please follow up with the teams and we'll continue here.
Yeah, I think so. That's
okay.
more important.
Yeah.
The presentation. Yeah.
So
Okay. So Arpan will follow up with you. So let me get then started. So we'll go into the second half. I hope all of you got an accounts and all. If there are any issues, please post it to the chat or Slack. We'll try to resolve those issues. So in the first half of the tutorial, you saw all the basic concepts of the parallel and distributed training, machine learning, and the task. So now let's flip the things a little bit and try to get a very quick overview of the high performance computing architectures. So as you can see, I mean, these days, if you take a look, I mean, we are in a hot interconnect conference. There are a lot of clusters are being deployed. Many of you are familiar with the top 500 systems. These are designed with multi-core, many-core processors, high performance interconnect, accelerators, and also the SSDs. So two types of things we want to understand a little bit before we go into more details. One is the hardware architecture, especially the interconnects and processors like the domain specific processors and communication middleware. So we'll just try to touch a base a little bit of these two concepts, and then we'll try to take a look at the solutions, like how people are designing the solutions for deep learning, machine learning, and data science. So on the on the interconnect side, many of you must be familiar now with InfiniBand. This technology has been there for 20 years. OmniPath has been also there for many years. High-speed Ethernet, RDMA over converged enhanced Ethernet RoCE. So all these networking technologies are providing very good performance. So these days, technology is there from node to node, you can actually have even a less than 1 microsecond. And InfiniBand SDR, you can actually get 200 gigabits per second. And a lot of these modern networks actually provide offload. So that means they have intelligence in the adapter. So when you perform the communication, just for communication protocols, there is very low CPU overhead, 5 to 10% kind of things. Then software stacks like OpenFabrics, LibFabrics, UCX, all these are also available. So that's how people are trying to deploy very large scale systems. Traditionally, these systems were deployed for HPC, but now AI workloads have become very common, and that's what we'll be trying to evaluate it. By the way, in the afternoon, in fact, myself and one of my colleagues, Dr. Harish Subramani, we have a full half-day tutorial on high-performance networking. So if some of you are interested, you can join that session. We'll really go into very details of all the technologies, protocols, InfiniBand, OmniPath, Tofu, all the networking technologies, whatever are available there, we'll go into many details. So here it just shows a very quick roadmap, as you know, just for one of the networks, like InfiniBand, we are in the HDR, but they have been proposing a NDR, which is 400, 800, 1.6 terabits per second. So all these technologies are there in the future. Now, while the networking technologies are helping to put together some commodity clusters, as many of you know, very dedicated systems or chips are being designed. So in this case here, we'll be seeing a hardware for DNA training and inference. These are the TPUs, the Google TPUs that has been there for several years. They have different versions. So the broad idea is that can a dedicated chips be designed to take care of a training and inference. Similarly, there is another product here is called IPU, Intelligent Processing Unit. So the idea is again very similar. As you can see with the different batches, with the ResNet 50 training, they were able to even show like a 10 to 100x speed up. And Microsoft Azure actually has some of these IPU instances. Recently, 2 additional products which are becoming, it is generating a lot of news, is the Gaudi, Habana Labs. So this is the training accelerator called Gaudi. So it has actually the AI processor is integrated with the Rocky. There is a Gaudi software. It was actually presented in Hot Chips 19. So systems are actually coming up to be deployed with these. Similarly, some of you must have heard of also Cerebras. So that is actually a really large scale first generation wafer scale engine. It contains 400,000 sparse linear algebraic compute cores. You remember, like we talked about these convolutions. So those are the at the bottom of all the computation. So this chip actually, this is the world's largest chip with 2.6 trillion transistors and almost 850,000 cores. So this was again announced in the last year Hot Chips 20. This will be the next generation systems which are also being deployed to really accelerate this DNA training. So like this, a lot of new things are coming. I'm just trying to include some representative ones. If your favorite hardware, software is not included here, please forgive me, because we don't have time to go over all, but I just want to give a flavor, saying what are the issues, what people are working on. So now, once we know the hardware architecture and processor, as you saw from on the chat, like at the top level, we have ResNet 50, might be it is going through some TensorFlow, going through Horobot, but then it needs to actually link with some kind of a communication layer. Okay, because in that communication layer, you will be actually doing that MPI already use kind of operation. So this is where I want to touch few concepts which will get very helpful in the later parts. So first is, of course, the MPI, which is a message passing interface. So this has been there, like once I have a distributed system, so how do the nodes communicate to each other? So this is where the distributed memory model, or MPI, which stands for message passing interface, has been there in the community now for last 30 years. And of course, within the node, you can do shared memory communication. And then people have proposed for the kind of a hybrid, they call it partition global address space, or PGAS. So that means it is a logical shared memory. I have multiple nodes with shared memory, but across nodes also I can do shared memory, but this is logical. So it's not like a CAS coherent kind of things. And then in that context, people are coming up, there are solutions like OpenSPAM, UPC, Chapel, etc. Now, there were a lot of questions about this all reduce. So all reduce is like a collective communication pattern. So it's like an MPI. Let's say MPI does an MPI all reduce. It's an element-wise sum, data from all processes, and then there are multiple steps involved, and that very much dependent on the communication middleware, the underlying hardware architecture, to see how efficiently you can do that all reduce. So here, if you see from a logical point of view, each GPU might have some data here. This is like a send buffer before. So that means I have this data. Somehow this all reduce I need to do. So that means I'm reducing across element wise. So in the end, I want every receive buffer to have these values 4, 8, 12, and 16. Okay. So then there is a standard here, like MPI all reduce. So you just, all the GPUs, after they do the forward pass, you can actually call MPI all reduce. Then the underlying algorithm actually exchanges a lot of information and comes up with this result. And later on, we'll see in the next section, we'll show a lot of performance numbers, and whichever communication middleware or software with the hardware delivers the best performance for this all reduce will actually give you a lot of benefits in the DLL training. So in this context, we'll actually be trying to show you some numbers. Some of you might be familiar with this MWAPIS 2 MPI library project. This project we started, it's continuing for 20 years. We started almost the day one of InfiniBand. When InfiniBand came in 2000, October 2000, we were working earlier to that on Mirinet, Quadrix, And we're the very first ones to jump into InfiniBand. We had a first open source version of the MPI demonstrated at Supercomputing 02. And then it's continuing for 20 years. And currently this is being used by more than 3,200 organizations. Just from OSU site, we have like crossed 1.42 million downloads. The stack is also a part of Red Hat, SUSE, OpenHPC SPAC. It is empowering a lot of top 500 clusters over the last 15 years. We are also a partner of the 10th ranked TAC Frontera system. That is a pure CPU system. So we'll try to actually, in the next few slides, we'll show you, we have come up with an MPI driven solution. Okay, so as an end user, you don't have to learn MPI or anything. You might be running your TensorFlow, but TensorFlow somehow being connected to Horoword and MPI and effectively giving you very good performance and scalability. So in that context, in the MPI, because a lot of these operations, as you know, are using GPUs, almost in 2011, 10 years back from our group, we introduced a concept of Cuda Aware Mpi. Okay. And in fact, over the last 10 years, a lot of other MPI libraries are adopting that. So the broad idea is that, let's say if you have a GPU, like you are computing something here and you need to send the data from here to this GPU. So traditionally what happens is people write if you are familiar with the CUDA programming, you will be doing a CUDA copy, MPI send, MPI receive, and then CUDA copy. So with those kind of multiple steps, you may not get very good performance. So around 11 years back, we worked closely with NVIDIA. NVIDIA introduced called GPU Direct RDMA, GDR. Some of you might have heard of this terminology. So the idea is that instead of going through CPU, can we directly go in through the InfiniBand, because InfiniBand adapter and GPU are sitting in the next to each other in the PCI bus. Can the data directly go transferred here and then go here? And that leads to very good performance. And in fact, that helps for the end users to in fact just write MPI send, MPI receive from GPU buffer and to GPU buffer. Everything else, as you can see, is taken care by the underlying MPI library. It automatically finds out what is the best possible path and gives you the communication with very high performance and with high productivity. And so look at the numbers here. So if you use a library like this is like trying to say the GPU to GPU internode latency. That means we are sending data from GPU of one node to the GPU of other node, and not in the same node. And we can deliver it like a 1.85 microsecond. Okay. If some of you are familiar with like an InfiniBand, takes around 1 microsecond to send data from CPU to CPU. Now we are with the GPU, we are able to do it at that fast rate. So not only it gives you a significant benefit in the latency, but it also gives you benefit in the bandwidth, bidirectional bandwidth, and all those lead to very good communication performance. Now, while these kind of things are going on, NVIDIA also has introduced the Nickel communication library, NVIDIA Collective Communication Library. Again, the motivation was also for deep learning. In the beginning, they had only a Nickel one, that is within a node with multiple GPUs, but now it has gone across with a Nickel 2. So that is also a very common communication library, which is being used in the machine learning, deep learning world. And in fact, in some of the case solutions, in the next section, we'll try to actually compare with Nickel. And we can show that MPI-driven solutions actually can deliver you, in fact, better performance and scalability compared to even the Nickel-based solutions. So that is the kind of the very quick overview of some of the technologies we just want to touch upon. But the main thing is that once these technologies are evolving, what are the kind of challenges? Okay, we talked about all these machine learning, deep learning, data science. It needs a lot of computation, needs a lot of communication. So how we can combine the HPC and this together? And this is what in my group, we are also been working on along this research for the last many years, and the community is also working along that. So we'll try to identify broadly 4 broad challenges, okay, in this field. And then in the next section, we'll try to provide some solutions to those. So the first thing is think of like this. So we have the deep learning, machine learning frameworks. We talked about these TensorFlow and all. On top of these, you might have your end application, like a pathology application or an image recognition application. Okay. And then we have we talked about all these model propagation, forward, backward, pass, and gradient aggregation. So all these, if you take a look at the framework, and these has certain memory requirements. The model requires some memory, it has some computation requirements, it has some communication overhead. So how do we take care of that? Okay, that is the kind of the first challenge. We need to make sure that communication is very fast. Computations, memory requirements are handled. So in a traditional HPC, if you think of like, let's say weather forecasting, like a WRF, when you are trying to run it on a big system, you need to make sure that communication is balanced. Everything is the frequently used data is fitting into the memory. Communications are happening properly. Load balancing is happening properly. So all those issues are also valid in this domain. So here, instead of the end application, we may need to see that, yeah, TensorFlow is being balanced properly. TensorFlow is running with a good communication performance. Okay, so that's the kind of the first direction of research. So in order to support that, of course, we need the communication runtime. And here I talked about all the different CPUs, GPU, TPUs, networks like InfiniBand and all. So the question is, in order to do the distributed training, we need to have a very high performance and scalable communication runtime. Okay, and if we can design such a thing, we'll be able to overcome the limits of single node training and then gradually scale to large number of nodes. So those are the second direction research challenge. The third direction goes inside the communication runtime. I talked about a little bit of CUDA awareness, but we also saw these collectives like all reduce. Of course, if you take a look, traditional HPC collective has been there for many years. It is not only all reduce, bcast, all-to-alls, gather, scatter. Those who are familiar with MPI, you will see there's a very lot of focus on optimizing all those collectives. So now the things have changed a little bit. If let's say HPC all reduce, people used to do like 8-byte all reduce. But now if you do a DL training, it could be 8 megabytes or even 8 gigabytes all reduce. Okay, so that means you need to come up with newer kinds of algorithms. Okay, and this is where this issue comes, like a large message collectives, and now instead of CPU, now you need to do GPU. So this is where all these MPI driven solutions, nickel based solutions, we didn't go into details like a glue, MLSL. So a lot of alternative solutions are coming up for the communication, trying to design the communication runtime in a strong manner. And then the final challenge is a co-designing. Okay, and this co-design is not a new concept. It has been there in the HPC field for many years. That means if I have a network or hardware, some communication middleware, software, and then applications, instead of looking at it in a layered manner, can we make changes here? Can we make changes here? Can we make changes here? And then work them all together to get the best performance. And same thing is also happening in this domain. So these are the kind of the broad 4 research challenges. If you are a student or if you are looking at where people are working on, you can classify all the research in the high performance deep learning or high performance machine learning or high performance data science into these 4 directions. Any questions here on the hardware, software, middleware, and the challenges?
I have a question.
Sure.
So
please.
it looks like NVIDIA is coming up with all these different, is using the frameworks and also the way to work with all these tools, which optimizes their systems to parallelize the algorithms of machine learning. So it's a changing world, right? Continuously, it looks like.
Yes. Yeah, so this is not just NVIDIA. I mean, the same thing is Intel is trying to do, same thing is IBM is trying to do. So this is the new era, okay? So because if you think of all the MLDL workloads, as we discussed earlier, the challenges, so how do you really deliver systems? And when I say system, it could be commodity systems, or it could be even dedicated systems. So this is where all these vendors are trying to push their efforts to come up with the systems which will really deliver very high performance and scalable solutions for the next generation MLDL data science, or in general, we can say AI solutions.
So yeah, so in order to pick up on these tools, which which uses all this underlying technology, thousands of hours of work of others. Basically, how do you approach like Intel or one of these companies, right? Telling them that what is your top one you're going to use, or it's not this is the right approach. I should say, I want to do this. What is your best tool for that?
So exactly the next section actually will talk a little bit, help you. Okay. So it's just like, think of like you are trying to buy a car, am I right? You have some requirements. Okay. Then you go into different dealers and then see which car satisfies your requirements. Right. So now you can think of exactly like this. So you have a certain kind of deep learning or AI applications or requirements, then you need to see which one of these solutions will work for you as they are, or if not, what needs to be done. So then you can talk to them. Okay. So the next section exactly will go into some of the common DL solutions, ML solutions, DAS solutions, whatever are available as of now. So you should be able to either download or set up your own systems to keep moving with your requirements.
I see.
Okay.
Is application-based approach versus okay, so you're saying basically based on my application, I should use like
I mean, that is one way if you really want a very dedicated system. Otherwise, if you have a bunch of applications, it's just like, think of like a HPC systems, how people deploy over the years. Am I right? HPC, again, you might have some 10 common applications. Think of an HPC center. So 10 common applications, then they evaluate different kinds of hardware, interconnect, CPU, GPUs, and then see which configuration will work good for them.
I see.
Okay? It is no different. It's no different. It is exactly similar things. Now you need to take into your newer requirements from the AI angle.
I see. Thank you.
Okay. Yeah. So with this, let me hand it over to Arpan. He will go into some of the solutions, and I hope people have been able to log in and then getting started. So then we'll go into after the solution section, we'll look at some of the open issues, and then we'll talk about the hands-on exercises. Any questions? Somebody has raised hand. Please proceed. Yeah.
Excuse me. Thank you for the tutorial so far. It's very informative and practical. And I'm a graduate student at Queens. I work with Ahmed Afsay, and I already know the 3 of the 4 categories of the research that you have talked about. But I didn't really understand what is the co-design research area is about, and what are the challenges that we're looking for, improving and utilizing them.
Yeah, so I can give a little bit of high level. I think one of the solution, Arpan, I believe we deleted it because of the time. So take a look at like we have done in our group, like let's say you take a cafe. So we have actually an OSU cafe version. Okay. So the cafe, the way it was trying to execute the lower layers were not very efficient. So in fact, we made some changes to the cafe. We made some changes to the MPI, and then we were able to give very good performance and scalability. So that's what we're talking here, co-designing. That means working across the layers.
Thank you. Yep.
Okay. Yeah. Any other questions? Okay. If not, Arpan, please take over.
Yeah, sure. Thank you, Dr. Panda. So I will try to answer your question in the subsequent slides also, Amit. So we have several case studies in this section for the deep learning. And broadly, these case studies are divided into 2 categories, data parallelism and model and hybrid parallelism, as they target different kinds of the models. Okay, so as I have said earlier also, like data parallelism is suitable for the models that can fit inside the memory of a single GPU. Okay, so if you want to train a model that fits inside the memory of a single GPU, then you can use the data parallelism. Otherwise, you have to use the model or the hybrid parallelism. So in the data parallelism, we will talk about the NVIDIA Nickel and the distributed training for TensorFlow and PyTorch. How can we do it on them? So let's start with the Nickel. So unfortunately, some of the researchers and engineers are introduced to Nickel before the MPI. some of the newer ones. So they ask the question like, why do we need MPI when we have the nickel? Well, the question is wrong. The question should be other way around, that why do we need nickel when we have the MPI? Because MPI has been here for last 30 years and it is empowering several HPC applications. So the question should be like this: why can we use the MPI? So this is the graph which used as a which was used as a motivation for the nickel at that time, like around 2017, when the nickel team or the NVIDIA team explored the distributed training. They saw that the MPI is not scaling well. So here they were using the DGX system, which had 8 GPUs. So they had several of these boxes. So when they on a one box, they were getting a very good performance with the MPI, but when they scaled it to multiple boxes of DGX, they found that the MPI is not scaling well. Like this is the idle scaling, this is the linear scaling, and you can see that MPI is somewhere here. So they said that the MPI is not good. We need to fill this gap, and so that is why they proposed the nickel. So that they can get a very good scalability. So, however, they never revealed the name of the MPI library they were using, because at that time, most of the implementations like OpenMPI were not optimized for the large message collectives. So traditionally, the MPI libraries are optimized for HPC workloads. So in HPC workloads, we don't have very large messages like 4 MB or 128 MB 128 MB for the communication primitives like call reduce. So that is why they were not optimized, and they were doing it on the GPU. And at that time, the GPU communication primitives were not also optimized. So that is why they saw this performance. However, now this is the recent study. So here we are showing that if we use the MRPIS2 GDR, which is a GPU-based solution for MPI, so it can offer a better performance than the nickel. So this is across all message ranges. So here we are showing the result for the short messages. So here we are showing that we are up to 4.7x better than the nickel. Obviously, this is not the use case where the nickel is designed for. So this is like this is the message ranges where most of the HPC applications are, and here the MPI provides a very good performance. However, in the next graph also we are showing the performance for the very large messages, where we are showing that we are up to 2.5x better than the nickel, or we give the similar performance. So nickel is you can imagine the nickel as a patchwork for a problem that was relevant in that time, like around 2017 or 2018. But nowadays, the MPI implementations are optimized for this kind of a workload. So that is why the MPI can provide a better or the similar performance as the nickel 2. So here we are showing the performance on the 1536 GPUs on the Summit supercomputer, which is the second fastest supercomputer in the world. So here you can see that we are also performing better than the nickel. And in terms of the bandwidth, like when it comes to the large messages, you want the highest bandwidth. So that is why we are showing the numbers in terms of the bandwidth also. And then for a particular message size like 128 MB for all the GPU range, for all the GPUs. So this is where, so now let's talk about the distributed training for TensorFlow and PyTorch. So how can you do the distributed training? What are the libraries you need to do the distributed training in TensorFlow and PyTorch? So let's talk about the TensorFlow for a moment. TensorFlow is very optimized, it's a very good framework for a single node or a single processing element. It gives you a very good performance, but when it comes to the distributed training support, it's not very good. Over the years, it tried to jump between different implementations. So that is why there is a lot of fragmentation when it comes to the distributed training or the data parallelism support. when I'm talking about the distributed training, I mainly mean the data parallelism. Okay, so it is started with the gRPC, like it resides in a different dimension than the MPI or the HPC workload we are used to. On the HPC system, so we normally run the parallel applications using MPI or the Slum or some other libraries, but the gRPC resides in a different dimension. And the one problem with the gRPC is also that it is not optimal. The communication, it was taking too much time for the communication. So this is where you can also see that why the nickel or the NVIDIA team wanted to have the nickel. Okay, so that is why several researchers have worked in this area. So they proposed accelerated gRPC. Our lab also worked on this, and we proposed accelerated gRPC to accelerate the communication. Now, the another option is to bootstrap the gRPC. Just add another communication runtime into gRPC that will be used for the communication. So there are different studies like gRPC plus MPI, gRPC plus verbs, or gRPC plus GDR. Now the last approach is let's get rid of gRPC. Okay, we don't need gRPC. We can implement our own solution in the TensorFlow and have an efficient one, and we can use any communication library we want. So this is the approach used by the Baidu and the Horoword. So Horoword is by the Uber. Uber is not a software company. It is a they don't want to design the software, but when they try to train a model, when they try to train the model on multiple GPUs, they saw that the distributed training support is not very good. So that is why they implemented the Horoword, and now the Horoword is a very popular middleware for the distributed training. It separates two things, like it separates the deep learning framework and the communication runtime. So at the upper layer, it provides support for the PyTorch, TensorFlow, and MXNet, and you can use any communication library with it. So it has support for the MPI, Nickel, Glue, MLSL, and DDL from the IBM. So it has a support for most of the communication runtimes we have nowadays. So that is why the Horoword is becoming very popular and gaining a lot of traction in the distributed training community. So here we are presenting a MPI driven infrastructure for MLDL training. So if you want to use the TensorFlow, PyTorch, or MXNet, you can just use the Horoword. These frameworks also have their native support, but Horoword has efficient implementation of data parallelism, and it has other optimizations also, like overlap of communication and computation, tensor fusion. So somebody asked, like, what is the core design? So here the core design is you can improve the data parallelism support in the deep learning frameworks also, like by implementing the tensor fusion, by overlapping the communication and the computation. So in this way, you can improve the deep learning framework, and on the communication side, you can improve the all reduce operation. So this is what we meant by the co-design. So if you, on the other hand, if you want to use the PyTorch, you can use the torch.distributed module also, which is a native support for the distributed training. And you can also use the DP-Speed, which is another distributed training middleware. So we have two different libraries for GPU and CPU. The MUP is to GDR for the GPU, as it is. So GPUs have different challenges than the CPU. So that is why MUP is to GDR is for the GPU. It is optimized for the GPU. And since CPU have different challenges and also orthogonal problems, so research problems, so that is why we have the MUP is to X for the CPU training. So what kind of the performance you can expect from this? So you can see that when compared to the nickel, MUP is to GDR can give you a very good performance, like it can give you the 9% higher, or and also it gives you the better scaling efficiency. And this is the result on the Summit supercomputer with the 1536 GPUs. And you can see that we can process up to 1.2 million images on the ImageNet 1K dataset. So that's like you can train a model on the ImageNet 1K dataset in just 4.5 minutes. That's very impressive. So now let's talk about the CPUs. So GPUs are good. We all know that GPUs are GPUs trains the deep learning model faster than the CPUs. But yeah, CPUs are catching up. So you can still train the model on the CPUs if you have a lot of them. So if you train the model on Tech Frontera, which has Cascade Lake processors on 2048 CPUs, then you can train it in just 7 minutes. That's not bad compared to GPUs. Yeah, you can train it in 4.5 minutes on the GPUs with less number of GPUs, but you can do the same thing on the CPUs also. So they are not behind if you use the correct set of libraries. So now let's talk about the model and hybrid parallelism. So data parallelism, model and hybrid parallelism are for the models that cannot fit inside the memory of a single GPU. So the models like the GPT-3 or the AmoebaNet, they are very big. If you want to train such model, then you cannot use Horoword or any data parallelism implementation. So here we are talking about the GPy, which is a solution from the TensorFlow. So it divides the model. Across multiple machines and then do the distributed forward and backward pass. It introduces the pipeline parallelism. So it is just borrowing the concept of pipeline parallelism from the computer architecture and implementing it in the distributed training to get the better performance. So please go to this link if you want to know more about the GPy. And now the next one is the FlexFlow. So FlexFlow identified the more dimensions of parallelism in DNNs and developed strategies and graphs for the parallel training. So it is kind of a search algorithm for finding the best parallelization strategy. FlexFlow is a deep learning framework. It is not a middleware. It is a deep learning framework, and you can train a model in this framework. So similarly, we also worked in this area. So here are a few case studies from our lab. So this is the Hyperflow hybrid parallelism for TensorFlow, which combines the data parallelism and the model parallelism along with the pipeline parallelism so that you can train very, very large model on CPUs. There are some models that cannot fit inside the memory of a single CPU also. If you want to train such models, then you can use the hybrid parallelism for TensorFlow, which is this paper was published in ISC 20. So here we are showing the speed up with the Hyperflow, and you can expect up to 481x speed up on the 512 Cascade Lake processors. So that's very good. Now, if you want to do it on GPUs, then we also worked in this area and presented the GPU-enabled memory-aware model parallelism system. That is like if sometimes you can only fit even on 4 GPUs, you can only train a model with one sample because of the memory limitation. So how can you solve this problem? This paper tries to solve that problem, and it was published in Supercomputing 20 conference. So please take a look if you're interested. So here we solved a real world problem using the GEMS. So in OSU, we have a digital pathology department, and they had a problem like they had a pathology images which were like 100,000 into 100,000 pixels. So obviously they cannot fit the entire image into one GPU memory. They cannot even train it with the 1,000 pixels. Like they had to train the model with very small pixel images like 256 or 512. So that is why we worked with them, and using the GEMS, we were able to train the model on the larger tiles to get the better accuracy and diagnosis. We decreased the training time from 32 hours to just 27 minutes using our implementation. So now the last case study is the super. So far I have talked about the convolution neural networks. If you want to speed up the training for the transformers, how can you do it? So this paper was published recently in the IPDPS. So actually my whole PhD is on the distributed DNA training and the parallelization strategies. So this is one of the paper. And you can see that we have different types of parallelism in the transformer model. So that is why we try to use those parallelism to get the better speed up. This solution is implemented in the LBAN. Someone asked earlier also what is the LBAN. So this solution is implemented in the LBAN deep learning framework from the Livermore National Laboratory, and it is available for your use. Okay, with this I conclude the deep learning solutions. Let me know if you have any question. Any questions? If not, Amir, can you please
Sure, Arpan.
present ML solutions? Yes, I can.
Okay. So now we start talking about some of the ML solutions that we have developed. So in this context, we have briefly talked about the Qml library. I'll talk about this again. This is from NVIDIA as part of the project, Rapids project, and it aims to build an end-to-end data science analytics pipelines on GPUs. So that is the goal of the NVIDIA Rapids project. And one of the important components of this project is the Qml library. And this library can be thought of as the GPU accelerated version of Scikit Learn, so GPU counterpart of Scikit Learn. And what essentially this does is that it supports the execution of machine learning workloads on multi-node, multi-GPU systems. So this might come as a surprise for you that Scikit Learn, which is a very popular machine learning framework, it has been around for, for actually decades, more than a decade. It's been around for maybe 20 years. And it doesn't have support for GPUs. So the conventional wisdom has been that the machine learning algorithms or workloads, that they are not as compute intensive deep learning or deep neural networks. And this is the reason that, these maintainers of Scikit-Learn, for example, they have not been very keen about, having solutions for GPUs. But what Qml has actually shown is that if we implement these algorithms for GPUs, there is still, some performance that we can obviously achieve by porting these, machine learning algorithms for Qml. Again, this is the point, this last bullet point is also trying to make that most existing ML libraries, including Scikit-Learn and Apache Spark MLIF, they only support CPU execution of machine learning algorithms. And this is the conventional wisdom that I just mentioned. So here are the main components of the Qml library. I'll just focus on the right-hand side picture at the top. So with most of the frameworks today, Qml library provides an interface in Python to the end users because Python is easy to learn. People are used to that. So at the end of the day, the Qml library does a lot of the work in C or C++ layer at the native level, trying to get maximum performance out of the hardware. But when it comes to exposing the interfaces to the users, it is possible to use Qml from C++ through C++ interfaces. But most of the users are going to utilize Python. And in this context, Qml designers have made an effort to come up with interfaces that are very similar to Scikit-Learn. And then the next level in the software is essentially this algorithms layer, where Qml developers are adding support for machine learning algorithms like regression, k-means, and random forest. And there is a long list of other machine learning algorithms out there as well. And the bottommost layer here is the primitive. So for example, which support primitive operations on GPU, something like, element-wise operations. Let's say we are going to do a sum, a product, matrix multiplication, eigen decomposition. So these are all different linear algebra primitives that are used to implement machine learning algorithms. So it's quite possible that you might need an algorithm that is not currently implemented in Qml. So then this primitives layer is providing this facility that we can rely on these primitives to implement our own algorithm at the algorithms layer. So another view of the Qml software is as follows. So at the top is Python, and followed by all the Qml algorithms and primitives implemented at the C++ layer. And this obviously makes use of the Cuda platform, which is the library by NVIDIA to make use of their GPU platforms. So the Python layer obviously interacts with the native C++ using something called Cython. So Cython allows the Python programs to invoke C++ functions. And when it comes to communication, so Nickel is actually committed to or uses Dask using the UCX communication device. And if it's doing collective communication, then it will rely on the Nickel communication device. And this is a view stack of the vanilla version of Qml. And what we have done as part of this work is that we have actually taken this software and we have added support for MOPH2 GDR, which is our GPU-based MPI communication layer in the Qml software stack. So again, as you can see, this is the similar the architecture that we have seen before. So there is a Python layer which talks to C, C++ where, which basically is the main workhorse layer in the Qml layer. This has all these algorithms that we are interested in, and it also provides support for primitives. But now in addition to Nickel and Dask and UCX, what we have done is that we are using Mpi for Pi, which is a wrapper Mpi library written in Python. We are actually now provided support for parallelization using MOPH2 GDR. So we have some results comparing Nickel with MOPH2 GDR, and as you can see in this slide, we are presenting numbers for k-means, linear regression, nearest neighbors, and truncated SV. So these are some of the machine learning algorithms available in Qml. And as you can see, we are actually seeing better performance for MOPH2 GDR as compared to Nickel for almost all of these algorithms. And these gains become, obviously, they are more noticeable when there are more number of GPUs, and hence there is essentially more communication going on at the Qml layer. So this paper has been published as part of ML HPC workshop last year, which is part of SC, and I would invite all of you to please go and have a look. MPI, so this software has also been, our solution for Qml is also available as a software from our HiDL website. So please, you can go and download the software and give it a try. Are there any questions related to ML solutions? So if there are not, then I will now talk about some of the Dask solutions that we have developed. So as I mentioned, I briefly introduced Dask, and Dask is a big data computation framework, just like Ray or let's say Apache Spark. So by default, it comes with two communication backends, TCP and UCX. And what we have done as part of this work is that we have developed something called Mpi for Dask, and Mpi for Dask, just like Mpi for Qml, is an MOPH2 based communication backend for Dask. And this is the first Mpi based communication device for Dask. And what this does is that it optimizes CPU and GPU communication in the Dask framework on modern HPC systems. Here is the architecture of the Dask software. So at the top layer is the Dask interfaces like task bag, Dask array, Dask data frame, delayed, future. If you're writing a program using Dask, these are some of the features that you will get exposed to. Under the hoods, what Dask Runtime does is that it converts your program into a task graph, which is then executed in a parallel way on HPC systems. Dask also has a rich ecosystem. For example, there are projects like Dask Mpi, Dask Cuda, Dask Job Queue, and they all facilitate executing Dask-based jobs on HPC systems. The most important layer in the context of communication devices is the Dask distributed layer. And this is the layer which also provides this notion for scheduler, workers, and clients. If you recall from previous material, these are some of the entities that enable parallel and distributed computing using Dask. And when scheduler is talking to worker or client over the network, it obviously utilizes some kind of communication. And this communication layer is also part of the Dask distributed. As I mentioned earlier, TCP is an existing device, UCX is an existing device, and we have added support for Mpi for Dask in the Dask distributed layer. So what this does is that Mpi for Dask makes use of MOPH2 GDR communication library through Mpi for Pi, which is a Python interface to the Mpi standard. I will jump to some of the results that we have. So here I'm presenting, this is benchmark one, sum of Cooper array and its transpose. So on the left-hand side, we are plotting the total execution time for the application. And on the on the x-axis, we have the total number of Dask workers. So each worker is executing on a single GPU. So as you can see, so this blue line is through TCP over InfiniBand. So we call that IP over IB. Yellow line is UCX based communication, and this red line is basically MPF for Dask. And as you can see, as we increase, if we compare red with yellow and blue, the MPI communication device is performing, much better on average, 3.47 times better on average than, the UCX communication device. And this gain is also visible when we try and plot the communication time. For communication time, the gains are more pronounced. This is like 6.92 times better on average. So in the hands-on session, we will actually try and run one of this application as well. So this is a sum of Cooper array and its transpose on the track Frontera GPU system. And here, this is more number of GPUs are involved, right? So the previous slide only had results until 6 workers, but here we are plotting results until 32 GPU workers. So as you can see, the MPI communication device, the red bar is outperforming all the other ones. The gains are less pronounced because they differ from system to system. They're like 1.71 times better on average than the UCX communication device. So this is another application, CUDF merge, and these are the results on track Frontera GPU system. And as you can see, we are performing like 2.9 times better on average than the UCX based communication device. So we have done a release of this software MPF for Dask from our own website. So I would invite all of you to go and download the software and please give it a try. And there is a paper published about this in CC Grade 2021. So the paper, a preprint version of the paper can be obtained from this particular link. So with this, if there are any questions, I'm happy to take any questions on the Dask or ML solutions that we have discussed.
Yes, I have a question. So you mentioned about Apache Spark, and it was in context of using Scikit Learn and run on a CPU. So between Spark and Dask, I'm a little bit confused. Is it Dask used mostly for GPU and Spark for CPU?
Right. Okay. So see, so Spark and Dask, they are two different ecosystems, two competing big data frameworks. One typically, targets Java and Scala programmers, but recently Spark also has support for Python. And Dask is basically targets, both. It only targets Python developers. So my discussion was in the context of that these big data frameworks, they traditionally have relied on CPU, but more and more they're relying on GPUs. So there is now support for Dask on the GPUs, and there are also efforts going on for Spark as we speak right now.
On a GPU, okay.
Yes.
Okay, thank you.
I will hand it over to to Dr. Panda now.
Yeah. So can you see my screen?
Yes.
Okay. So we are running out of a little bit closer to the finishing time. We still have hands-on. Let me spend a few minutes on some of the open issues and challenges being faced by the community. So these are the kind of the 5 open issues. I'll go one after another. So through the presentation, you would have now seen there is a lot of convergence is happening from the ML, DL, data science, and HPC. People are asking, is ML, DL, data science, and HPC problem? Why HPC can help? Obviously, these are all just like the traditional grand challenge problems. The next generation applications are all these machine learning AI. So definitely HPC can help. We saw a lot of examples. And some of the needs are exactly the same match. These are compute intensive problem, communication intensive, IO intensive problems. So whatever the HPC systems have done in the past to accelerate the HPC applications, the same systems can be used even to help with these next generation applications. And we talked about, like, of course, some of the communication runtimes, etc., need to be updated. We talked about large message communication, Cuda Aware communication. And we also talked about all these scalability issues. We talked quite a lot about this large batch size helps improve the scalability, but there is always a limit to the large batch size. And because you want to make sure that you are trying to take advantage of the overlap at the same time, the latency hiding. But while this field is evolving, the DNN sizes are increasing. Here, if you take a look at, this is a really large model, 137 billion parameters. And this is a new direction which is coming because you cannot fit everything into the GPU at any given time. So in that context, the question is how we want to fit into the GPU. Arpan mentioned some of the solutions, what we are working on. The community is also working on some of the solutions. These are called out of core training. So that means if you cannot fit everything in the model and the data in the GPU, how efficiently you need to come up with some solutions. And in that context, there are a lot of different solutions out there. In fact, we are one of the very early ones we had a called out of core cafe. I'll not go into details. You can take a look at this. We presented this at the HiPC paper, but more and more solutions are now coming, and especially NVIDIA's the managed memory concept. Some of you might be familiar. You can actually move, let's say you are not, even though I have a large model, you are not working on all the layers at any given time. So then you need to do some efficient orchestration so that only those layers which are being worked on reside on the GPU at any given time. And then behind the scene, you can actually bring things from the memory to the GPU or GPU to the memory. And while all these things are going on, people are also have been talking about standardization. Okay. Nowadays, there are a lot of different solutions, different frameworks. There's a lot of competition going on, but that is natural. Anytime a new field comes up, this is what exactly happens. If some of you are in the HPC field in many years, you would have seen even before MPI came into the picture, exactly same thing happened. There are a lot of, every company had their own communication library. Then that led to competition, but it also led to problem that you cannot port your application from one system to the another. So this is where I think the field is also entering this phase. People are also trying to see how we can standardize these, how we can standardize benchmarks. There are a lot of work happening. The one thing which is getting a lot of momentum is the ML part. Some of you must have heard of it. So this is where they are trying to standardize, just like in the CPU side, like let's say spec MPI, similar kind of effort is taking place in the ML perf, so that can there be some standardized way to report performance number across different applications and systems. So then there is a lot of things are happening. There was a question on the Slack earlier. With all these different solutions, how do we handle the portability, or how do we handle accessibility? So there are two things happening here. One is the OpenAI. So here you actually will be getting a lot of different models are there. If you are trying to build your own things, instead of trying to start from scratch, you should be able to go and then get some of the models which are already available, trying to build on top of that. Similarly, there is an Onyx format which is being worked on. So let's say you have done all your training using TensorFlow, and now PyTorch is gaining momentum. Can that model now be used again for the PyTorch environment instead of starting from zero? So this is where you can take a look in the Onyx format. It is an open format to exchange the 10 models. So different vendors are actually trying to add their converters there. So those are with respect to the DLs. The same thing is happening, exploiting GPUs and unified communication layers for data science frameworks. Amir mentioned about this. There's a lot of work taking place in the Rapids, Accelerator, the Spark. There was a question just now, and Amir answered this. So the issues at the bottom line is very similar. Again, how effectively we can do GPU to GPU communication, because all these software stacks are built on GPU. So any of the this is where, in fact, in our group, as you saw, we are trying to proceed with the MPI driven solution, because MPI is a very generic middleware. It has been there for many years. It will be there for many more years on all the systems. So if you can exploit the use of the MPI library, then you should be able to achieve a very good, not only good performance and scalability, but also portability. So that is the kind of the direction where we are going on. So then what I'll try to do, you have set up the hands-on exercise. I hope all of you logged on. But in case some of you have constraints, what we'll try to do is, let me first forward a little bit, officially conclude the tutorial, but we'll be here. So we'll work with you, those of you who are interested in the hands-on, and then we'll see how many things we can cover. So let me first forward, just officially finish it. So as you saw, we had a short time, effectively like 3 hours, but within the 3 hours, we started like from 100,000 feet level and trying to take you to the very lowest layer. And then with the hands-on exercise, we'll really take you to the ground zero. But overall, you will get an idea that there is exponential growth is happening. All these ML, DL, data science, or AI, we try to provide an overview of all these issues and challenges, and we'll take you through a set of hands-on exercises so that you can get a feel for these. But overall, you actually need entire this field, okay, need a lot of collaborative efforts. This is the field still blooming, starting from the hardware vendors to the softwares to the application vendors, the cloud providers. Everybody needs to work together to provide a full-fledged solutions. So with this, I'd like to thank all our sponsors. What we are trying to bring you here is a work of almost 20 years. And a lot of students and staffs have contributed all to these efforts. So every time we make a presentation, I always salute to these my heroes. So the work has been going on for so many years, and everybody contributes to what you have seen today. So these are our web pointers. If you have any additional questions and all, please feel free to send us notes. We'll be very happy to answer those questions. If there are any quick questions people would like to ask now, we can spend few minutes, and then I'll suggest Arpan to start the hands-on exercises, and then we'll see at least few labs we can do it. And all these lab scripts, the machines are available today. We have another afternoon tutorial, but if some of you are interested, you can continue to work on yourself. And whatever the scripts and all we have provided, these are open source. Please feel free to use it on your system or any other targeted systems to carry out your exploration along these topics. Okay. So I'd like to say formal thank you, but we are not closing. We'll switch to the hands-on now. Any questions? Okay, Arpan, please.
Yes, sure.
Start.
Give me a few seconds. I hope you can see my screen with terminal and the presentation on the right.
Yes.
Okay, great. So now let's start with the hands-on exercises. So lab 1 was all about setting up the environment for distributed training. So it's an optional lab. So we have already set up an environment for you so that you can run the distributed training with PyTorch and the TensorFlow. So you don't have to worry about it if you are not able to complete the lab 1. All the instructions are available in the README file. Let me show you also. So 1 second. So initially you will be in this directory. If you open the lab 1, actually lab 1 is the only lab which has its separate README file. So these are all the commands you need to install HoroWord, PyTorch, and MPI. So you can follow these things. So basically we are also installing the mini conda so that you don't have to rely on the native Python support or the installation. So let's go with the lab 1. Let's try to run the lab 2, sorry. In the lab 2, we are going to run the DNN training with the PyTorch. So basically here we will use the HoroWord example scripts. So HoroWord has example scripts for to test the environment. So we are going to use those scripts. So if you go to the lab 2, please copy all the commands from the README file available here. So if you see here, we have the commands for the lab 2 here also, PyTorch. So just copy this command and you should be able to run it. Go to lab 2 and just paste the command and it will run. So let me tell you what are we running. So it is just a batch script. So what command are we running here? We are running this command. Okay. So here we are showing that this is just the Python implementation, the absolute path to the Python installation. And then this is the benchmarking script. That's it. And we are giving the batch size of 64 and number of iterations 5. So this is a benchmarking script. So that is why it is showing the performance in terms of images per second. Here we are training the model ResNet 50 with a batch size of 64 on one GPU. And we get around 334 images per second. So this is a V100 GPU with 32 gigs of memory. Okay. Are you able to run this lab? Let me know if you face any issue. So I will jump to the next task, that is multi-node with mvapis2 GDR. If you open the README file, this is the command for the mvapis2 GDR, run with mvapis2 GDR. So you can just copy this command and run it. So when you run this command, now the run command is little bit longer. So here we are using the Mpi run RSH. So Mpi run RSH is just a job launcher. So it is just like the Mpi run. We are creating two processes on GPU 01 and GPU 02. And these are the some flags for required for the mvapis2. They are common. Okay. So after that, we have the benchmarking. Sorry. After that, we have the benchmarking script. This one, absolute path to the benchmarking script. And then we are training with the batch size of 64 per process, iterations 5. So here you can see that we are getting almost the double the performance. So we are getting around 1.9x performance on 2 GPUs. If you go to a higher number of GPUs, it will sustain. So this is for the lab 2. And the lab, you will see the similar thing for the lab 3. I will skip the lab 3 for now so that we can focus on the ML exercises. So in the lab 3, we were supposed to run the TensorFlow, same method, just copy the command and you will be able to run the distributed training with TensorFlow. If you're interested in actually training a model like the MNIST data, training a convolution neural network on the MNIST data set, then we have a homework for you also that is available here. If you go to the last, I think it is here, 1 second. Yeah, here is the homework. So if you want to train an actual model, you can do it on the single node using this command and using this command on the multiple nodes. Okay, thank you. If you have any question, please let me know. Amir, you can take over from here.
Yes, thank you. Right, so Arpan, can you see two screens?
Yes, yes.
Oh, two windows, sorry. Right, yes, so yes. On my left-hand side, I have the README file open, and I'm actually doing the ML labs, which is lab 4. And on the right-hand side is the terminal. So I'm logged in as one of the users, one of the accounts that we have provided you. So I just, copy and paste the commands. I'll go to the right folder by using this command. And once here, I am inside the Qml or the machine learning library lab folder. And in this case, you will see a bunch of these scripts that can be used to launch the different applications. So I will just take the command task 1. And in this task 1, what I'm doing is that I'm running the k-means algorithm on 1 GPU, right? So I will just run it. And this is now basically going to use the Qml software, and it will also use the MPI communication backend that we have developed and train this k-means, essentially do the cluster identification using the data set that we have provided. We have actually provided it this many number of, this is like 250,000 more than that number of data points. and now it's basically, it has essentially returned the results. So I can also do this with 2 GPUs. So this is task 2 of lab 4. So I can, run this using 2 GPUs. Again, I'm using the same script. If you're interested in learning, the details, so this script is very critical because it gives you all the details, like what exact command has been executed, how did we set up the environment. So please do look at that. So this will now return the results, and we will see that using like the DL labs, using 2 GPUs for the machine learning tasks, it will also result in twice the speed that we basically get. So with this now, I will now move towards lab 5, which is the task section. And in the task section, I will let this job finish first, and then I can start talking about this. So basically, there are 2 tasks in the lab 5. And in lab 5, as you can see, we have we have task 1 and task 2. So the task 1 is mostly setup. So you just need to simply, copy and paste the commands. So I will just copy this. This is, I just created a new folder, and I will execute the second command. This is going to copy the lab material into a temporary folder for you. So this will help you in essentially going and customizing the code. So this is the code I will be executing. So you can go and look into this with detail. So as part of task 2, we basically show running Dask using TCP first, but I'll skip that. I will just go and change the source code to start using the MPI for Dask or the MPI communication backend. So I will just change that, and I'm basically now doing task 2C. So I will just take this command and I will run this. So this is the exact command that it's executing, and it's actually starting 4 MPI processes. It will start the scheduler, 2 workers, 1 client, and these workers are essentially going to do computation for you on the GPUs. And as you can see in the slides, that we actually get around 3.4x time. So you can try it yourself, and when you are going to compare performance of, let's say, TCP communication device with MPI based communication device, you will see that you will experience around 3 to 4 times the speed ups, which is actually pretty substantial. So with this, as you can see, we are executing this benchmark several times, and we executed this 5 times, and the median wall clock reported here is 4.04 seconds. So if you have any questions, or if you wanna, feel free to contact us on the Slack channel. So I'll just stop sharing and I'll hand it over to Dr. Panda for the close up of the session.
Yeah. So thanks a lot again, Amir. I hope all of you learned significant things from this tutorial. Again, these topics are so huge. We try to put together things in a coherent manner so that we can really take you from a 100,000 feet level to the ground zero. As I indicated again, if you want to continue with the hands-on exercises, please feel free to do so. The machines are still reserved. We'll use it for the afternoon tutorial. And I told in the earlier, myself and Dr. Hari Subramani will go into present this high performance networking tutorial in another 1 hour. So if you are interested, please feel free to join that. There will really go down into all the networking protocols and all the open issues and challenges. So if there are any final questions, we'll be very happy to answer. Otherwise, we can close it here, and we can always talk offline through the Slack. Any other question, final questions, comments?
One question on the labs. Do you use, if you want to copy the script files, should we use the .sh files and also the README file. Those two will be enough, I think. Is it something else that I need to copy?
In order to
run,
go ahead, Amit. Go ahead.
Yeah, in order to run in my own environment.
We would encourage you to actually use these scripts and the README file to run the examples here. But we have, it's not just these scripts and the README file. It's actually a lot of installations that we have already done for you.
Mm-hmm.
That environment is actually not visible to you.
I see.
So it's actually more than that.
Okay.
And for the DNN training, we have an exercise on the environment setup also. So you can follow those instructions. And we have sent a link to the Ideal website also, where you can find the detailed instructions to set up all these environments for the distributed DNN training. So once you have that environment, then you just have to replace the paths in the script and you should be able to run them. Okay.
I see. So the DNN training is correspond to which lab?
Lab 2 and lab 3.
Okay, thank you.
And lab 1 is all about setting up the environment. Okay.
Mm-hmm. I got it.
So in fact, let me quickly share the Ideal site. Actually, it has all the details, user guides. Might be one of you, Amir, or somebody can share quickly.
Yeah, I can do it.
Share quickly. So these are the periodic software releases we have done for the all the QML, for the Horovod training, and also for the on the Dask. We have it on the big data page. So if you go to any of these pages, you will get all the details with the details, user guides, and all those things.
So I have just shared a user guide for the Horovod on the Ideal website. Here we have the detailed instructions to install PyTorch, TensorFlow with Horovod, and you should be able to install them very easily.
Yeah, so this is the website, high performance deep learning website. So if you go here, you should be able to, it has all the information. Okay. So MPI for QML, even the OSU Cafe I talked about, the user guide, and then on the high BD, sorry. So on this site, you will be able to find out the MPI for Dask release. Again, all the user guide, everything is here. So you should be able to, whatever we talked here or whatever you are doing hands-on, you should be able to recreate it on your systems and use it for your applications. And of course, the MPI libraries, whatever we talked from our group, those are all available here from the MAPS project site. So these are all the MAPS to GDR, MAPS, everything is available here. So these are the three main websites. If you follow those links, you should be able to be very proficient on running your ML, DL, data science applications. Any other questions, comments?
Hi, is it possible for you to keep the session logins available for tutorials over the weekend?
That might be very hard, actually. I mean, so this is a shared cluster. We have like 100 people using this cluster. So we just borrowed some time. It's not just from our group, it's a department-wide cluster. So that will be hard, but it will be available until 6 o'clock tonight.
Okay, thank you.
Okay, yeah. Any other questions, comments? Okay, so if not, then I'd really like to thank you, all of you, for spending time with us, and we'll be starting the next tutorial in another 50 minutes. Thank you. Bye.
Thank you.
Thanks to you. Thank you very much.
Bye. Yeah, bye.